Welcome to Brain Vision.
So here we're going to say that the angular acceleration, by definition, would be the derivative of the angular velocity with respect to time. And we know that the initial angular, we're simply going to say that we're going to assume that the acceleration is constant, and then we can say that the angular speed at time equals 0 is omega initial. Therefore, we're just starting at t equals 0 seconds. And this would just set up these boundaries for the integral that we need to take. So if we start off by this, we can say that d omega, my apologies, would be equal to alpha dt. At this point, we can integrate, and we can say that the integral from omega initial to omega final of d omega would be equal to 0 to t, assuming that t is starting at 0 seconds, of alpha dt. At this point, we can solve, and so this will become omega final minus omega initial. This will equal alpha t. And solving for omega final, this would simply be equal to omega initial plus alpha t. So that's how we derive this equation. Now, furthermore, we know that we can say that omega final would be equal to omega initial plus alpha t. So just rewrite this. However, this is going to equal the change in angular displacement with respect to time according to the definition of angular velocity. We can then algebraically manipulate this and say d theta will equal omega initial plus alpha t times, again, dt. And now we have to integrate once again. Integrate from 0 to theta of d theta. This would be equal to the integral from 0 to t for omega initial plus alpha t times, and we find that theta, the change in angular displacement, would be equal to omega initial times t plus 1/2 times alpha t squared. So this would be how we were to derive the equation for the change in angular displacement. That is the end of the solution. Thank you for watching.